In this video, we consider another example on how to test hypothesis on two populations using independent samples. This example reads as follows. Researchers wondered if there was a difference between males and females in regard to some common annoyances. They asked a random sample of males and females the following question. Are you annoyed by people who repeatedly check their mobile phones while having an in-person conversation? Among the 551 males surveyed, 205 responded yes. Among the 522 females surveyed, 213 responded yes. Does the evidence suggest a higher proportion of females are annoyed by this behavior? Please note the statement of what we want to test. The question, does the evidence suggest a higher proportion of females are annoyed by this test, by this behavior? That is the goal here. So to begin with, question A requires us to determine the sample proportion for each sample. Since the emphasis here is on the proportion of females, I'm going to let population 1 be the population of females and population 2 be the population of males. So as it stands, I'm interested in, for the population of females, the sample size we selected, N1, is 522. And out of that N1, X1 equals 213 responded yes. Whereas for males, the total surveyed was 551, so N2 will be 551, and out of that 551, X2 equals 205 responded yes for males. So in this case, I can use this to get the sample proportion for each of the sample. Sample proportion here is P1 at, and that will be X1 divided by N1. This will be 213 out of 522, which is equal to 0.4080. And the sample proportion for the second group will be P2 at, that is X2 out of N2, that will be 205 out of 551, which is equal to 0.3721. So we have our answer for the sample proportion for each samples. Those are 0.4080 for females and 0.4321. Question B. Explain why this study can be analyzed using the methods for conducting hypothesis tests regarding two independent proportions. First of all, take note that the sampling here is independent sampling. The ladies who were, or the females who were surveyed, have no connection as far as the information provided is concerned, or have no connection with the females that are surveyed. So here you have independent sampling. Then some other important parts are as follows. As we said earlier, the samples are independent. The second reason is that N1 times P1 at times 1 minus P1, if you multiply all of this, is at least greater than 10. Similarly, N2 times P2 at times 1 minus P2 at is also greater than 10. You can work that out and verify that. Then the sample size is less than 5% of the population size for each of the samples. So we proceed to question C. What are the null and alternative hypotheses? Let P1 represent the population proportion of females who are annoyed by their behavior in question, and P2 represent the population proportion of males who are annoyed by their behavior in question. Well, if that is the case, let our H0 be the null hypothesis and H1 is the alternative hypothesis. Remember, I will suggest or recommend starting with your null hypothesis. And that is because we have a statement of exactly what we want to test. We want to see if the proportion from females, which is P1, is it higher than those suggested by the behavior from males, which is P2. So we want to check if P1 is greater than the proportion that we observed from the population of males. So this will be P1 greater than P2, whereas this will be the hypothesis of equality. With that part of the question completed, we move on to question D, where we are required to describe the sampling distribution of P at female, which we are represented as P1 at minus P2 at, the sample proportion from the population of males. And we have to draw a normal model with the area representing the p-value shaded for this hypothesis test. First of all, to note, the sampling distribution follows a normal model, has a normal distribution, or is modeled by the normal distribution, and it looks like the normal distribution. The mean is definitely 0. Why is that so? That is because if you look at what you have here in the alternative hypothesis, P1 equals P2, if I subtracted P2 from both sides, on this side, I will have P1 minus P2, which is equal to P2 minus P2. Since it's the same, this is 0. So we are hypothesizing that the average difference is equal to 0. That is the mean. And then the standard deviation of this estimate is given by standard error of P1 at minus P2 at. This is equal to the square root of P at 1 minus P at multiplied by the square root of 1 all over n1 plus 1 over n2, where our P at here, take note, this is not P1 or P2. It is just P at. P at here is equal to x1 plus x2 divided by n1 plus n2. So we need to first get this piece first, then we'll serve it into this formula. So let's proceed to do that. What is our x1 and x2 in this case? Our x1 and x2 is 213 plus 205. So 213 plus 205 divided by n1 plus n2 is 522 plus 551. So 522 plus 551, which is equal to 0.3896. Right. And now that we have this piece, take note that this piece is what is going back in this shaded part. I still need the N1 and N2 here. So I'm ready to get the standard deviation. So I'm going to pull this over here. This is equal to the square root of 0.3896 times 1 minus 0.3896 multiplied separately by 1 over N1. N1 we saw earlier is 522 and 1 over N2, which is 551. Please be careful while working on this. Do not throw the whole bunch into the calculator at once. It will give you errors, more likely than not. If this computation is well done, you will certainly get 0.029785545. It suffices to take it to just about 4 decimal places, 0.0298. That works. So, in this case, what we have is a mean of 0 and a standard deviation of 0.0298. So this means that the point of inflection here, where it starts to drop, we'll have mean minus this value, or mean plus that value. So you have 0.0298 there. This is the normal model that represents the sampling distribution of this estimator. All right, so with that said, we proceed then to another part of the same question. We continue the same question. We are to find the test statistic for the hypothesis test and to determine the p-value for this hypothesis test. How do we do that? A quick note that I just remembered in the previous part of the question. Please note that since this is a right tail test, this has to be shaded to reflect that this is on the right here to represent the normal model. So with that said, we continue to what we're working on here. So take note, earlier we noted that our X1 was equal to, for females, it was 213 out of 522. And that was for population 1. And then for the second sample, X2 was 205 out of 551. So, and we're conducting this test at what level of significance? So if we look back, in this case, we would observe, if we look back, that the alpha was not provided here. I would like you to use alpha equals 0.01 level of significance. All right, with that said, let's take that to StatCrunch. So in StatCrunch, let me pull StatCrunch out. I'm going to edit this quickly, or just to remind you, let's start fresh. Go to Stat, go to Proportion Statistics, go to One Sample with Summary. And in this summary, we want to key in for the first population, 213 out of 522. So I'm going to do that, 213 out of 522. Then for the second sample, it is 205 out of 551. So 205 out of 551. And then for the hypothesis part, I want to ensure that this is right tail. Why is that? That is because what we set up earlier was greater than. And then next, I would like to show my critical value, and the level of significance in this case is 0.01, the alpha. So compute, and I have these pieces here. So here from the results, I can see my test statistic and I can see my p-value. So I'm going to take that back to my working bench. So here I have the test statistic and I have the p-value. Along with the test statistic, I always recommend remembering to indicate the region of your rejection region. So since we are dealing with P1 minus P2, this is greater than, so this would be on the right side of the test. That is where your rejection region is. And the value that cuts it off is provided, or has been provided, as a critical value. This is 2.326. So I'm going to put that here, 2.326, which immediately tells me something. My test statistic is 1.21. This is definitely lesser than 2.326, so it does not fall in the rejection region, which means I am not going to reject the null hypothesis. If I am not rejecting the null hypothesis, what do I observe here? So this is immediately telling me I'm ready to draw a conclusion. That means since 1.21 does not fall. Let me write this and then pick up from there. So as we mentioned earlier, the test statistic value does not fall in the rejection region, which is the shaded region here. So that tells us that since it does not fall in the rejection region, we respond with, we are also not going to reject the null hypothesis. In other words, we do not reject the null hypothesis. If we do not reject the null hypothesis, that is because the null hypothesis is the one we embrace. It is the good one. So going back to where we started, so this is the good one. This is not good enough. But remember, this is the one we wanted to test, which means if it is the bad one, it has to be that we do not have enough evidence in this sample data to back what we wanted to test up. So that is why we say, thus, there is insufficient evidence at the alpha equals 0.01 level of significance to suggest that a higher proportion of females are annoyed by the behavior in question. With that said, we proceed to the next concept, which is to learn how to construct and interpret confidence intervals for differences between two population proportions. In this case, we want to note that the sampling distribution of the difference of two proportions from independent samples can also be used to construct confidence intervals for difference of two populations. We do need the following assumptions to be true, which are pretty much the same assumptions we checked earlier when we were conducting a test of hypothesis on two populations. And then, once those conditions are met, we can use these formulas to compute manually the lower and upper bound of a 1 minus alpha 100% confidence interval for the population proportion 1 minus population proportion 2. Well, at this level, we're going to use StatCrunch technology to help us crunch out each of these numbers. So without any further ado, we take an example. In this example, we are asked, a survey asked, how many tattoos do you currently have on your body? Of the 1,221 males surveyed, 191 responded that they had at least one tattoo. Of the 1,014 females surveyed, 141 responded that they had at least one tattoo. We are required to construct a 90% confidence interval to judge whether the proportion of males that have at least one tattoo differs significantly from the proportion of females that have at least one tattoo. And then we are to interpret the interval. In part A, this is a breakdown of the requirements of the problem. We will let P1 represent the proportion of males with tattoos and P2 be the proportion of females with tattoos. If that is so, population 1 in this case for males and population 2 for females in this case. Then, in the case of males, the total males that were selected, N1 is 1221, X1 responded, and then for females, N2 was 1014. This is the sample size for females, and then X2 is 141. So we would like to construct a 90% confidence interval. To do this, all we need to do is go back to StatCrunch, and I'm going to close this and go to Stats, Proportion Stats, to Sample still, with Summary, and I'm going to key in those values. So I have 191 out of 1221. So I'm going to type that in, 191 out of 1221. Then for the second group, 141 out of 1014. So 141 out of 1014. Okay, so ensure that you have the right values in there. And then with that said, we would like to construct or perform a confidence interval for P1 minus P2. I'm going to change this to 0.90 because I want a 90% confidence interval. So with that said, if I like, I can show the critical value and compute. So as it stands, my lower limit is this negative value, and my upper limit is this value. So I'm ready to write that here on the next line. Okay, so my 90% confidence interval will be So here on the screen, I've carried over those values we got. Values we got from StatCrunch. So you have the lower limit and the upper limit. And with that said, we were ready to interpret the interval. Let us write that down. The interpretation of this interval is as follows. It's a 90% confidence interval for the differences. So this means that there is a 90% confidence that the difference of the proportions is in this interval. Please note immediately that this interval goes from a negative number to a positive number, which means it crossed what? 0. 0 lies in this interval or in this range of numbers. Anytime this interval contains what? A 0, it is immediately telling us that the null hypothesis holds true in this case. That is, we don't have enough evidence. We don't have enough evidence in support of the alternative hypothesis. Remember, the null hypothesis is saying that P1 minus P2 is 0, which is the same thing as P1 equals P2 if I add P2 to both sides. And the alternative is saying P1 minus P2 is greater than what? 0. Well, since the interval contains 0, it means it can actually be 0. That means the null hypothesis holds true. That means we do not have enough evidence, or there is insufficient evidence of a big enough difference in the proportion of males and females that have at least one tattoo. Then we proceed now to the next example. In the next example, we want to illustrate how to read an output from a technology tool. In clinical trials of a medication, 2,152 subjects were divided into two groups. The 1,561 subjects in group 1 received the medication. The 591 in group 2 received the placebo. Of the 1,561 subjects in group 1, 55 experienced dizziness as a side effect, whereas in group 2, 17 experienced dizziness as a side effect. To test whether the proportion experiencing dizziness in group 1 is greater than in group 2, the researchers entered the data into statistical software and obtained the following results. We are to test these results at alpha equals 0.1 level of significance. Here are a couple of things to note. The green confidence interval and the other color p-value. If you observe closely, this confidence interval goes from a negative number to a positive number, which means it could be 0. That is, the difference between these two populations could be 0. What does this mean in everyday English? If the difference between you and I is 0, that means we are literally the same thing. So if the estimate for the difference can be 0, because 0 is contained in this range or interval of possible values, if it can be 0, it means you are, in other words, saying they are more likely the same. Then another thing to notice, in this case, our null hypothesis and our alternative hypothesis would have been set as follows. If we want to test whether the proportion experiencing dizziness in group 1, represented by proportion 1, is greater than that in group 2, it means the null hypothesis is P1 equals P2, which is the same thing as saying P1 minus P2 equals to 0. So in this case, if you observe the p-value to be 0.228, this is to be compared with alpha. We recall that since p-value in this case is greater than alpha, our p-value is 0.228, our alpha value is 0.01. Whenever this arises, we do not reject the null hypothesis, And that will be consistent with the fact that earlier, when we constructed a 95% confidence interval for this value, this was a value, right? We had 0 in this interval, which means the difference could be 0. So if the difference could be 0, this null hypothesis holds true. So as it stands, even if we use alpha equals 0.05 in this case, this is also greater. So in this case, we're not going to reject the null hypothesis. So since we do not reject the null hypothesis, it means that we do not have enough evidence for the alternative that we wanted to test. And that implies, by extension, that there is not enough evidence to conclude that the proportion experiencing dizziness as a side effect in group 1, represented by P1, is greater than those in group 2.